Dinocysts are abundant. Behind it, wood fragments are common. We can tell where in the system we are and whether the sands can be traced or correlated by recognizing which type of microfossils are present. The upper part of the reservoir is dominated by a huge tidal estuary, with spit development restricted to the western edge. As the Viking Graben widens, the Horda platform tilts towards the east. The 6 series sands show this clearly. Initially, the sands are prevented from reaching as far west as before, but as the fault blocks tilt even further, the crests become exposed as small islands, and the older sands are eroded. Gradually, they redeposit as narrow beaches. These are called Sin Rift sands, sands actively formed during the rifting of the Viking Graben. In essence, this is what a cross-section of the formation looks like. Layers upon layers of different sands, very much like tree rings, marking growth through time. And it's in these sands that we find the oil and the gas. During the Jurassic period, we see a variety of life, from the great dinosaurs to microscopic organisms inhabiting the seas. Microscopic plankton are found in abundance and give nourishment to life in this period. But as we'll discover, these will also provide energy in the distant future. The plankton, so abundant near the surface of the sea, will eventually die and sink to the sea bed. There, in oxygen-starved water, they form a thick layer of organic mud. In the Cretaceous period, these plankton become covered by further layers of mud and silt. This is a continuous process that creates layer upon layer, each characteristic of a different geological time. Gradually, their sheer weight will push the underlying sediments downwards, and an interesting process takes place. The organic muds are compressed into a compact black shale, the Draupner Formation. But the organic mud out in the Viking Graben is subjected to higher temperatures, as well as the burial pressure. This starts a slow simmering process, cooking the deposits until oil and gas is formed. We now have oil in the Viking Graben, but the Troll oil field lies on the Horda platform. Time would prove to solve this part of the puzzle. About 90 million years later, in the Tertiary period, something major happens out there below the sea. As the floor of the Viking Graben continues to sink and the fault blocks are tilted, sand layers that were previously separated now become connected. And this is what will enable the oil to migrate. As these different layers come into contact with each other, pathways are created through which the oil and gas can flow freely. In a strange twist of fate, some of the oil and gas become trapped underneath the very same organic material that they derived from, the cap rock of the Draupner Formation. So now we have an oil field. But as we can see from this model of the reservoir, the column containing the oil is extremely thin. At its maximum, it's only 26 meters in height, and throughout most of the field, it's as thin as 13 meters. To clearly see what's going on, we need to magnify the actual height of the reservoir. This will give us a better visual understanding of the reservoir and its geology. At the top, we have the sea, with water depths up to 300 meters. 1,200 meters below the seabed, we have the actual reservoir. Now, a typical reservoir contains gas at the top, here marked in red, the green oil column, and water at the bottom marked in blue. So how do we extract the oil? When first discovered in 1979, the estimated recoverable oil from the reservoir was zero. The conventional method of drilling vertical wells would not have enabled sufficient oil recovery to justify the cost. So in order to develop the field, a multitude of horizontal wells would be required. Right here in the western part of the reservoir, the first test well was drilled in 1989. The well was 500 meters long and produced over an 11-month period. In the following year, a further test well was drilled in the second fault block, where the oil was even thinner. The results were encouraging. Now, time would prove critical. The gas that provides the life-giving pressure to the reservoir is currently a valuable energy resource in itself and must be produced while a market exists. So the oil had to be extracted quickly before the reservoir pressure could fall below the critical level, causing the reservoir to die and sealing the oil in the ground forever. The challenge then was to place the horizontal wells in the highest permeability sand layers, those sands that would produce at the best rates. This is clearly illustrated by opening up the model at the oil-water contact. Here we see the elongated shapes representing the clean sands of the various phases of the spit development. Since the entire area has been tilted, we get this distinct pattern of the different sand bodies. Now that the test wells had confirmed the possibility of producing oil from the western part of the reservoir, field development started here. However, the potential of the central part, with its thinner oil column and more complex geology, was uncertain. Development of this part would demand both new drilling technology and new production techniques. One of the first challenges was to place the wells in the most optimal locations. For this purpose, geosteering was used. As the drill bit approaches the oil-water contact, the electrical resistivity of the reservoir gradually decreases. In addition, it's vitally important to stay within the clean sands. By measuring the gamma rays naturally emitted by the sands, we can tell whether the sands are clean or micaceous. Careful interpretation of the logs is essential to avoid an expensive mistake. Drilling long intervals in the permeable sands carries with it another challenge, the risk of getting sand in the oil flow. So purpose-built excluder screens are installed along most wells to prevent this. These enable the whole well to produce oil. This technology has been almost unique to Troll. As oil is produced, the pressure of the gas expanding above pushes the oil downwards into the horizontal wells. Over time, the oil column becomes thinned by production, and the gas-oil contact moves downwards. Gas breakthrough usually occurs after some months and results in significantly higher gas rates and lower oil rates. To delay gas breakthrough for as long as possible, wells are located progressively closer to the oil-water contact, often only half a meter above the water. But this brings with it another challenge. Increased amounts of water mixed in with the oil. Initial water cuts in Troll wells are typically above 50%, but can be as high as 85%. So tremendous effort must be put into both water management and water treatment. In wells experiencing production difficulties, the sea sands in the gas zone above the heel can be deliberately perforated in order to produce artificial lift. By introducing gas into the oil flow, the total weight of the well fluid is reduced, allowing the oil to flow out from the reservoir more easily. To understand the effects of the production over time, we utilize time-lapse, or 4D seismic, a newly applied technology where several seismic surveys are gathered